Good evening, dear students. I am Nanda Kumar of EC department from the Pallavi Engineering College. I am going to take the classes for DSP, that is Digital Signal Processing, of third unit, that is IIR Filter Design. By the end of this unit, you must be able to design any digital filter of IIR. So these filters are, a filter is nothing but which allows only the desired components or desired frequencies and which rejects all the unwanted frequencies. Here IIR refers to the infinite impulse response filters. Here filter is nothing but a digital filter. A digital filter must be a linear time invariant discrete time system, and there are two types, that is FIR and IIR. FIR refers to finite impulse response filters and IIR refers to the infinite impulse response filters. Impulse response, here the finite impulse response. What is impulse response? Impulse response is the response when you give impulse as the input to a system. The response you get from that system is called impulse response. When the response you got from that system is finite, then that filter is said to be a finite impulse response filters. And if the response you got as infinite, then the filter is said to be an infinite impulse response. So let us see some differences and let us compare the FIR and IIR filters. So as we have earlier studied that FIR is a non-recursive type. What is non-recursive means? Which doesn't have any feedback. And whereas IIR is a recursive filter. Recursive filter means which has some feedback. If you can see, if you can see the of difference equation of any system, where y of n is the output of a system, and the first term summation k equal to 1 to n ak into y of n minus k is the previous outputs of the system, and summation k equal to 0 to m bk into x of n minus k. This shows the present and previous outputs of the previous inputs of the system. As you can see from here, these are the present, if the system depends on previous outputs, present and previous inputs, then that system is called an IIR filter. If the system doesn't depend on these terms, that is previous outputs, it only depends on the present and previous inputs, then that system is said to be an FIR filter. So an FIR filter depends on the present and past input samples, but whereas an IIR filter depends on the past output samples and present and previous input samples.
To design an IIR filters, it must satisfy two conditions. One is it should be causal system and it should satisfy the stability condition. So an impulse response for a realizable filter should satisfy the causal condition, which is h of its impulse response h of n should equal to 0 for n less than 0. That is, for the negative values the impulse response should be 0, and it should also satisfy the condition of stability. When a system is said to be stable, it should satisfy the impulse response must be finite. That is, summation n equal to 0 to infinity mod h of n should be less than infinite. Next, we want to know the transfer function of the system. Of transfer function of the digital filters or system function is given by h of z, which can be found from the difference equation. We already know the difference equation is y of n is equal to summation k equal to minus sigma k equal to 1 to n ak into y of n minus k plus summation k equal to 0 to m bk into x of n minus k. If you rewrite this equation, if you bring this output terms to the left side, y of n plus summation k equal to 1 to n ak into y of n minus k is equal to summation k equal to 0 to m bk into x of n minus k. If you apply z transform to this, so y of n will become y of z plus summation k equal to 1 to n ak into y of z into z power minus 1, where y of n minus k, if you use shifting property of z transform, it will become y of z into z power minus 1, and the inputs summation k equal to 0 to m bk into x of k into z power minus 1. If you take the y of z as common, then you will get 1 plus summation k equal to 1 to n ak into z power minus 1, that is equal to summation k equal to 0 to m bk into x of z into z power minus 1. We know that transfer function or system function of a digital system is given by h of z is equal to y of z by x of z, which is output by inputs. If you take this term to the RHS side, then it will become summation k equal to 0 to m bk into z power minus 1 by 1 plus k equal to 1 to n ak into z power minus 1. This is the general form of the digital system. So transfer function of a digital system is given by summation n equal to 0 to infinity h of n into z power minus n, which is this term. Designing of an IIR filter for the given specifications means we have to find the coefficients, that is ak and bk, where ak is the input coefficients, output coefficients, and bk are the input coefficients. If you find those coefficients, then the filter is designed. So before going to designing the filters, let us first review the filters. Frequency selective filters. A filter is the one which rejects unwanted frequencies from the input signal and allows the desired frequencies. That means it allows only the required frequencies and which rejects all the unwanted frequencies. Or the range of frequencies that are passed through a filter is called pass band, and the frequencies which are blocked by the filter is called stop band. So those are called frequency selective filters, and these filters we will use in different applications, like in communications we will use for selecting the required frequencies. Let us take an FM radio. In that we will tune to one particular frequency. That means we are selecting some particular frequencies. There we will use some band pass filter. So the filters are of different types. There are, as we know that there are low pass filter, high pass filter, band pass filter, and band reject filter. Let us review the different types of filters. As we know that a low pass filter is a filter which allows lower frequencies to pass through it, and which rejects all the higher frequencies. That means which allows only the lower frequencies between 0 to omega c, where omega c is the cutoff frequency, and greater than omega c it will not allow. So greater than the frequencies which are greater than omega c will be blocked. In the filters also there are ideal and practical. What are ideal filters? Ideal filter is the one which has ideal characteristics, which has having sharp cutoff. That means there is no transition band. From here you can see that here the blue line shows you that the ideal characteristics, and the red line here shows you the practical low pass filter characteristics. On the x axis you are taking frequency, and on the y axis I am going to take the magnitude of the filter. And the frequencies which are allowed by the low pass filter is called pass band, and the frequencies which are blocked by the low pass filter is called stop band. And the cutoff frequency we will get at 0.707. You can see here at 1 by root 2, or if you take magnitude in dB, in decibels, then the cutoff frequency will get at minus 3 dB. The frequency at minus 3 dB or 0.707 or at 1 by root 2, that frequency we will take it as cutoff frequency. Okay. So there will be only one cutoff frequency for the low pass filter. It allows only the lower frequencies and which blocks the higher frequencies. While coming to the high pass filter, which will block the lower frequencies and which will allow the higher frequencies. So as we can see from the diagram that the blue color line shows you the ideal characteristics of the high pass filter, and the red color line shows you the practical characteristics. So after the omega c, only the filter will allow the frequencies. Below the omega c, the filter will block it. But because of practical filters, there will be some frequencies will be allowed in the stop band also. So our goal is to reduce the frequencies in the stop band to make the characteristics near to the ideal characteristics of the filter. As you can see here also, at 0.707 or 1 by root 2, we will get the lower cutoff frequency. In the low pass filter, we will have the higher cutoff frequency. There will be only one frequency for the lower pass filter and high pass filter. Whereas band pass filter, in the band pass filter, it allows only the certain band of frequencies between omega 1 and omega 2. Before designing the filters, we need to know that there are two representations of omega. One is like Greek omega, and another one is W. So these two are the representations of omega, and the first one, this represents for the analog filters. And this is for the, this omega representation is for the digital filters. Okay, we must follow these representations throughout the subject. So here this capital omega represents the digital filter, and this small omega represents the analog filters or continuous filters. So for the band pass filter, it allows only certain band of frequencies between omega 1 and omega 2. From here you can see that omega L is the lower cutoff frequency and omega H is the higher cutoff frequency. So it is allowing, there is pass band only between omega L and omega H. As there are two cutoff frequencies, there are two more frequencies which are WS1 and WS2. These are stop band frequencies, stop band cutoff frequencies, WS1 and WS2, and where WP1 and WP2 are pass band frequencies. WP1 is the lower cutoff frequency pass band, and WP2 are the higher cutoff frequencies. And the cutoff frequencies we will get at 0.707 or at minus 3 dB. While coming to the stop band reject filter or band stop filter, which band reject filter or band stop filter we call it as. In the band reject filter, it rejects only certain band of frequencies and which allows all the frequencies except certain band of frequencies. Here also you can see from this figure that between omega L and omega H, that frequencies are omega L and omega H are the cutoff frequencies for the band reject frequencies. So between omega and omega H there is no frequencies are allowed, and all the frequencies are allowed except this. And there is two stop band frequencies, WS1 and WS2. Similarly, WP1 and WP2 are the pass band frequencies. Before designing any digital filter, first we have to design the analog prototype for that, and then we have to transform that analog prototype to the digital filter. So for designing the filter, first we need to know the parameters. The main parameters we use are omega p, omega s, omega c, epsilon and lambda, where I will show you the specifications here on the paper. Take a look at that. Let us see the filter specifications. Okay, here these are we can specify the filter specifications in three different ways. One is for the analog filter and for the digital filter, and the alternate way of filter specifications. So first we will see the analog or digital filter specifications. This is for the low pass filter.
So from the specifications you can see that on the x-axis we have took frequency, and on the y-axis we took the magnitude h of j omega. This is for the analog, and h of mod of h of j omega for the digital filter. So as we can see, the maximum amplitude is at 1, and at pass band is till omega p. So this omega p, this pass band will get at 1 by root over 1 plus epsilon square, and there will be some transition band, and then we will get the stop band. So the minimum frequencies allowed are called stop band, at which we will get the stop band frequencies we will get at 1 by root over 1 plus epsilon 1 by root over 1 plus lambda square. At this point we will get the stop band frequency, which is given by omega s or omega s, and this is the stop band ripple. As minimum, stop band ripple should be as minimum as possible, and pass band ripple should also be as minimum as possible. This is the pass band ripple, and the attenuation from 1 to this pass band ripple, this point is called pass band attenuation, and till here it is called stop band attenuation. This is 0 to omega p is pass band, and omega p to omega s is transition band, and omega s greater than omega s it is called stop band, and if you want to find the transition band omega t, it is given by omega s minus omega p. And the cutoff frequency, you will get at 1 by root 2. If you want the passband frequency and cutoff frequency to be the same, then epsilon should be equal to 1. Then it is 1 by root over 1 plus 1 square. It is, we will get it as 1 by root 2. Okay. And the alternate way of specifying the filter specifications are like this, where epsilon is the passband ripple parameter, where lambda is the stop band ripple parameter, omega p is the passband cutoff frequency in radians per second, and omega s is the stop band cutoff frequency in radians per second. And in the similar way, we will specify the filter specifications in the alternate way. Here we will take delta 1 and delta 2 in the alternate way of filter specifications, where delta 1 is the peak passband ripple and delta 2 is the peak stop band ripple, where omega p is the passband frequency, omega s is the stop band frequency, and omega c is the cutoff frequency at 1 by root 2 or minus 3 dB or 0.707. Here also the same way how we have defined here, the same specifications here for the stop band frequency. Here we will take it as delta 2, and 1 minus delta 1 is equal to 1 by root over 1 plus epsilon square, or you can get the epsilon from delta as by using these formulas. Okay, where delta p is the passband ripple and delta s is the stop band ripple, where epsilon is equal to 2 into root over delta p by 1 minus delta p, and lambda is equal to root over 1 plus delta p whole square by 1 minus delta square by delta s. These are the specifications. By using these specifications, we will find the filter coefficients. Okay. Let us see some of the differences between digital and analog filters. So a digital filter is one which processes the digital signals and generates digital data, and whereas for the analog filter processes analog inputs, and analog inputs means it is continuous inputs and generates analog outputs. In the analog filters, we will use active or passive components like resistors, capacitors, transistors, like that, transformers. We will use in the resistors and capacitors we will use, and amplifiers. In the digital filters, we will use adders, multipliers, delay unit like a computer system or digital signal processor. And in the analog filters, if you want to change the frequency response, or if you want to modify the frequency response, you have to change the components physically. Whereas in the digital filters, we can modify by changing the filter coefficients. By changing the filter coefficients, we can change the digital filters frequency response. And we shall see some of the advantages and disadvantages. Digital filters are highly immune to noise, and it has high stability factor and it possesses considerable parameter stability. And whereas analog filters are easily attract towards noise and low stability. And in analog filters are influenced by component aging and temperature and the power supply variations. So due to these components, we will use some components in that. If by the age of the component, it will be affected by the noise, and if the temperature increase, the analog filter frequency response may change. Okay, and the disadvantages of digital filters are quantization error. Quantization error arises due to the finite word length, because when we convert the analog signal to the digital signals, we will quantize the signals by sampling. After the sampling, we will quantize the signals. So, and after quantizing, we will convert it to the digital signal and we will process it. Due to that, there will be some quantization errors. That is the only disadvantage in the digital filters. As we have discussed earlier, digital filters, before designing a digital filter, we have to design the analog filter and then we have to transform it to the digital filter. Let us know how to design the analog filter now. So to filter the analog filter, we need to know the transfer function of the analog filter. Also, transfer function of the analog filter is given by h of s. So as I said earlier, Laplace transforms are used for the continuous analog filters, and jet transforms are used for the digital. So h of s is given by the summation I equal to 0 to capital M ai into si by 1 plus summation I equal to 1 to n bi into si, where numerator part is indicated by n of s and denominator is indicated by d of s, where h of s is the impulse response or Laplace transform of h of t. Laplace transform of impulse response h of t. Okay. For a stable analog filter, poles of h of s should lie left off of the s plane, and there are two types of analog filters. One is Butterworth filter and another one is Chebyshev filter. So we will study in detail of the Butterworth and Chebyshev analog filters in the next class. Good night and thank you.